In this lecture, I want to go over some important notes about CGs, or center of gravities, and inertias. So I have this seesaw or teeter-totter set up. So I have the balance point, it's a rigid body set up to be passive, so it's not going to move. And I have the board on top of it, it's an active rigid body. And you can probably guess what's going to happen when I press play. It's going to fall down and just balance. If I move this object over a little bit along the Y axis, it's going to do what you expect also. It's going to rotate that way. And likewise, if I move it over this way, it's going to do the same thing. If we move over here, we have a slightly different setup. So if you were to guess what was going to happen in this case, you would say that there's a lot more mass on this side, so it's going to fall and then rotate that way. So let's see what happens. It doesn't. It falls the other way. And this has to do with the way Blender places the CG, or the balance point, of a rigid body. So if we click on this object, the balance point, or the CG, the center of gravity, is where the origin point is. And you can actually have the origin point anywhere for a rigid body. So here I have it way on this end. So that's why it falls that way. So if I wanted it to be balanced, I would need to place this on top of the center of the balance rigid body. And now it just sits there like it is balanced. And if I wanted it to fall the other way, I had to put it past there like that. And it's a little weird, and especially when you get into edit mode, because if I go into edit mode and I move things around like this, it's not moving the origin point. So I can move this way over here, and it's going to fall like the CG is unbalanced. Let me show you how that is. So if I put it right there, it's actually going to fall that way. And of course, you can recalculate the origin, or the CG, by just selecting the rigid body and doing origin to center of mass, or center of mass surface. Center of mass volume, or center of mass surface, like that. And the same thing with this one. All right, let's talk about moments of inertia. So here I have a motor. This is a rigid body setup. So I have a passive cube down here that's going to hold everything together, or from falling. I have a motor. This is a rigid body constraint. It's set up as a motor. And then I have the axle that it rotates about. And this is kind of a preview of how we're going to set up things in the future. And then I have this rigid body, which is active. It's going to be kind of like a propeller, a really short propeller. So the motor applies a torque, and it has a target velocity. So I'm going to bring this down, target velocity to 1. Well, I'll leave it at 10, but leave the max impulse at 1, or take the max impulse down to 1. And I'm going to press play. Let me set that at 10, actually. All right, you can see it speeds up until it hits 10 radians per second, which is the target speed. All right, let me make a copy of this and move it along here. And I'm just going to come into a top view. Let me rearrange these a little bit. Put that there. All right, so now I have two of exactly the same setups. So if I press play and let it run for, say, 60 frames about, you can see they both turn the exact same amount. So they're at the exact same angle here. But what happens if I scale this along the y-axis? If you know anything about physics, you would know that this one would have a larger moment of inertia. It's got the same mass, but instead of all the mass being concentrated at the center, like this one, the mass is more spread out. So if you were to apply the same torque to this one, it would actually speed up slower than to this one. And that's the setup we have right here. So if I press play, this one's going to have the exact same torque applied to it as this propeller. So let's press play and see what happens. So I run it for 60 frames, and again, they're at the exact same angle. So again, if you know things about physics, you might see something like this and think that there is something seriously wrong with Blender's physics engine if it can't calculate or take into account moments of inertia. And that would certainly be the case, except it's really just a result of the weird way Blender apparently calculates the moment of inertia. And that's because it doesn't take into account the scale. It only takes into account the original size, basically. So if I apply this scale, watch what happens. Now it speeds up a lot slower. And that's the correct result. So that's what you want to happen. So whenever we're doing rigid body physics, you need to apply the scales to all the objects. So just something to keep in mind when we're working through it, that the scale, whether or not it's applied, can have dramatic effects on how your simulation runs.